Introduction to DDoS Protection with IP Tables. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we're tackling one of the most critical aspects of network security: protecting your infrastructure from distributed denial of service attacks using IP tables. If you've ever had your server taken offline by a flood of malicious traffic, or if you're proactively preparing your defenses, this presentation will arm you with battle-tested techniques that can mean the difference between staying online and losing thousands of dollars per minute in downtime. DDoS attacks have become increasingly sophisticated and accessible to attackers. What used to require significant technical knowledge can now be purchased as a service for as little as $5 per hour on the dark web. I have personally responded to attacks ranging from simple SYN floods to complex multi-vector assaults combining volumetric, protocol, and application layer attacks. The techniques I will share today have successfully mitigated attacks exceeding 100 gigabits per second. While IP tables alone will not stop the largest volumetric attacks, those require upstream filtering at your ISP or CDN level. It is remarkably effective against the majority of attacks you are likely to face. More importantly, proper IP tables configuration can prevent your server from becoming overwhelmed even when under attack, maintaining service for legitimate users while dropping malicious traffic efficiently at the kernel level. Understanding DDoS attack vectors. Before we can defend against DDoS attacks, we need to understand how they work. Let me break down the main attack vectors you'll encounter and why each one requires a different defensive approach. Volumetric attacks are the brute force approach. They simply try to consume all available bandwidth. These include UDP floods, ICMP floods, and amplification attacks. The diagram shows how attackers use spoofed source addresses to make responses go to the victim. DNS amplification, for example, can produce a 70 times amplification factor. A 60-byte query generates a 4,000-byte response. NTP amplification can be even worse, with factors exceeding 500 times. Protocol attacks exploit weaknesses in network protocols. SYN floods are the classic example. They initiate TCP handshakes but never complete them, filling up your connection table. TCP connection attacks establish full connections but send minimal data, exhausting your server's connection limits. Fragmented packet attacks send overlapping fragments that consume CPU during reassembly. Application layer attacks are the most sophisticated. They complete proper connections and send seemingly legitimate requests, but at a rate that overwhelms your application. Slowloris keeps connections open by sending partial HTTP headers. HTTP GET/POST floods request resource-intensive pages. These attacks can be devastating with just a few hundred connections if they target expensive database queries. The real danger comes from multi-vector attacks that combine all three types. I once dealt with an attack that started with a SYN flood to distract us, then switched to DNS amplification to saturate bandwidth, and finally settled into an HTTP flood targeting our search endpoint. This is why our defense must be layered and adaptive. Rate limiting fundamentals. Rate limiting is your first line of defense against DDoS attacks. The hashlimit module is incredibly powerful but often misunderstood. Let me explain how to use it effectively. The hashlimit module creates separate tracking buckets for each unique identifier, whether that's a source IP, destination port, or combination of factors. Unlike the older limit module which applies globally, hashlimit gives you per-source rate limiting. This is crucial because you want to limit each attacker without affecting legitimate users. In the first example, we are limiting each source IP to 25 connections per second with a burst of 50. This stops single-source floods while allowing legitimate traffic spikes. The source mask of /32 means we track each individual IP. If you set source mask to /24, you would track entire subnets, useful when facing distributed attacks from the same network. The second rule implements SYN flood protection. We limit SYN packets to 2 per second per IP with a burst of 5. This is aggressive but effective. Legitimate users rarely need to open more than 2 new connections per second to your server. The hashlimit htable expire parameter is important because it determines how long idle entries stay in memory. Too long wastes memory. Too short might reset limits for slow attackers. The recent module shown in the third example takes a different approach. Instead of token buckets, it maintains a list of recent source addresses. Here we are blocking any IP that sends more than 20 packets in 60 seconds. The update flag resets the timer on each match, while check tests without modifying. This is perfect for creating temporary automatic bans. One critical lesson I learned: always whitelist your monitoring and management IPs before implementing rate limits. I once locked myself out during an active attack response because my SSH session triggered the rate limits. SYN flood protection strategies. SYN floods remain one of the most common DDoS attacks because they are simple to execute and devastatingly effective against unprotected servers. Let me show you multiple layers of defense that work together. First, we enable SYN cookies at the kernel level. This is your safety net. When the SYN backlog is full, the kernel stops storing half-open connections and instead encodes the connection state in the sequence number. Legitimate clients complete the handshake normally, while attackers' spoofed packets are silently dropped. The TCP max SYN backlog increase gives you more buffer before SYN cookies activate. The iptables rules implement progressive rate limiting. Notice that we first check if the source is already marked as bad, mark 1. If so, we drop immediately without further processing. This is crucial for performance. Why waste CPU cycles analyzing traffic from known attackers? The return target is used strategically to exit the chain early for legitimate traffic. The SYN proxy target is particularly clever. Instead of passing SYN packets directly to your application, iptables completes the TCP handshake itself. Only after verifying the client is real does it establish a separate connection to your server. This completely isolates your application from SYN floods but adds latency. I typically use it only on specific ports under active attack. The invalid state rules catch a variety of protocol violations that often indicate attacks. The FIN and SYN combination is impossible in legitimate traffic. New packets without a SYN flag suggest connection hijacking attempts. The careful ordering of these rules matters. You should check connection state before rate limits to avoid penalizing established connections. In production, I've seen these rules handle sustained SYN floods of over packets per second on modest hardware, keeping the actual server load under 10% while maintaining full service for legitimate users. Connection limits and thresholds. Connection limit controls are essential for preventing resource exhaustion attacks. Even if attackers pass your rate limits, they can still overwhelm your server by opening thousands of connections. Let me show you how to implement intelligent connection limiting. The conlimit module counts concurrent connections per source. The first rule limits each IP to 80 total connections. This might seem low, but legitimate browsers rarely need more than 6 to 8 connections per domain. Setting conlimit mask to 32 means we count per individual IP. Change it to 24 to limit per /24 subnet, which is useful against distributed attacks from cloud providers. Port-specific limits are crucial. SSH should never need more than 2 connections per IP. For example, one active session and perhaps one SFTP web servers can handle more, but 50 concurrent connections per IP is generous, even for aggressive crawlers. The combination with hashlimit in the HTTP rule provides both connection and rate limiting. The global port limit using statistic module is a last resort defense. When more than 10000 connections hit port 80, we randomly drop 75% of new connections. This maintains some service availability even under massive attack. The random mode ensures the dropping is distributed rather than sequential, giving all users a chance to connect. The progression is important. First apply per IP limits, then per service limits, finally global limits. This creates graceful degradation as the attack intensifies. Service quality decreases but doesn't completely fail. I've used this pattern to keep e-commerce sites partially functional during Black Friday combined with DDoS attacks, maintaining enough capacity for purchases while dropping aggressive bots. Always monitor connection counts during normal operation before setting limits. I once set the HTTP connections limit to 20 and broke a customer's AJAX-heavy application that legitimately opened 30 simultaneous connections. Use SS-TAN state established or WC-L to check current counts and set limits at least 2 times your peak legitimate usage. Advanced packet filtering techniques. Beyond rate limiting, we need to identify and drop malicious packets based on their characteristics. These filters catch attacks that try to fly under rate limit thresholds by sending low volumes of specially crafted packets. The string matching rules detect application layer attacks. The first rule catches a specific user agent used by the Low Orbit Ion Cannon, or LOIC, attack tool. The hex string match finds base 64 encoded shellcode, which is common in exploitation attempts. String matching is CPU intensive, so we limit it to the first 100 bytes and only for new connections. In one incident, these rules caught a sophisticated attack that was sending exploit attempts at just 1 request per second per IP. Well below rate limits but still dangerous. Geo-IP blocking is controversial but effective for certain scenarios. If you run a regional business, why accept traffic from other continents? The example shows blocking entire countries, but you can also whitelist only specific countries. I helped a European e-commerce site reduce attack traffic by 90% simply by blocking non-European IPs during an attack. The restore mark ensures we only do geo-IP lookup once per connection. Length-based filtering catches many automated attacks. Empty packets, oversized packets, and specific sizes often indicate attack tools. The 40-byte rule catches SYN packets with no options. This is uncommon in legitimate traffic, but common in attack tools. Packets over 1400 bytes might indicate amplification attacks. I discovered one attacker always sent exactly 666-byte packets. A simple length match blocked their entire campaign. Packet validity checks catch protocol violations. The rules verify correct TCP flag combinations, reasonable header values, and proper packet structure. Invalid packets are almost never legitimate, and consuming CPU to process them is wasteful. These rules alone can drop 30 to 40% of attack traffic with near zero false positives. The key is combining multiple detection methods. Attackers might randomize one characteristic but rarely randomize everything. Layer these filters for defense in depth. Dynamic blacklisting and whitelisting. Static rules aren't enough for evolving attacks. You need dynamic lists that adapt to attacker behavior. IPset is the key to managing these lists efficiently, even with millions of entries. The automatic blacklisting system works in stages. First, HashLimit identifies IPs exceeding rate limits and marks them. Then we add those marked IPs to a temporary blacklist using the SET target. The timeout ensures IPs are automatically removed after 1 hour, preventing permanent blocks from temporary spikes. The source configuration means we match a source IP address and then add that source IP address. For more complex scenarios, you could also match a destination and add a source. The whitelist must be checked first to prevent blocking critical services. Always include your monitoring systems, payment processors, CDN IPs, and management networks. The accept target with no further processing ensures whitelisted IPs bypass all security checks. I learned this lesson when our rate limiting blocked our payment processor during a flash sale, costing thousands in lost sales. The fail2ban integration automates response to application layer attacks. When fail2ban detects multiple 404 errors, failed logins, or other suspicious patterns in logs, it adds IPs to the blacklist. The example shows the IP table's actions, but the real power is in failed to bands log parsing. I've written custom filters for WordPress attacks, SQL injection attempts, and API abuse. Managing these sets requires automation. The monitoring script checks set sizes, removes old entries, and alerts on unusual growth. A blacklist growing by thousands per minute indicates an active attack. The backup script is crucial. I've seen blacklists with entries lost to server crashes, immediately re-exposing the server to all previous attackers. Performance is excellent with IP set. Checking an IP against a million entry set is 0-1 with hash sets. Compare this to checking a million individual IP tables rules, which would be ON. This efficiency lets you maintain extensive blacklists without performance impact. Protocol-specific defenses. Different protocols require different defensive strategies. Let me show you optimized defenses for the most commonly attacked services. HTTP protection goes beyond simple rate limiting. The request rate limit of 10 per second might seem aggressive, but remember this is per IP. Legitimate users rarely exceed this. The connection limit of 20 handles browsers that open multiple connections. The key addition is request size limiting. Many HTTP flood tools send massive POST requests to consume bandwidth and processing time. Limiting POST requests to 1 megabyte stops these, while allowing legitimate file uploads on specific endpoints. DNS servers face unique challenges. The query rate limit must be set carefully to avoid blocking recursive resolvers that proxy many users. That is why we allow 50 queries per second, which is higher than for other services. The string match blocks common amplification queries. ANY queries are rarely legitimate anymore and are commonly used in amplification attacks. The response rate limiting in the output chain prevents your server from being used as an amplification source. SSH requires the strictest protection since it is your management interface. 2 connections per IP is plenty. 1 for terminal, 1 for file transfer. The recent module creates a temporary tar pit. After 4 attempts in 2 minutes, that IP is blocked for the remainder of the 2-minute window. The aggressive 2 SYN per minute limit might cause legitimate reconnections to fail briefly, but it is worth it to stop brute force attacks. SMTP is interesting because you need to balance security with mail delivery. The connection limit prevents connection exhaustion, while the rate limit stops rapid-fire spam attempts. The burst of 10 allows for brief spikes when legitimate mail servers deliver queued messages. I've seen attacks that open 1000 SMTP connections and hold them open with NOOP commands. The connection limit stops this cold. Each protocol configuration was refined through real attacks. These aren't theoretical limits but battle-tested values that balance security and usability. Monitoring and detection. You can't defend against what you can't see. Effective DDoS protection requires comprehensive monitoring to detect attacks early and assess your defenses. Let me show you how to build visibility into your IP tables protection. Logging is your first detection mechanism, but naive logging will kill your server. Never log dropped packets directly to syslog without rate limiting. I have seen servers die from disk input/output on log writes during attacks. The NFLOG target sends packets to user space where you log D2 can process them efficiently. The prefix helps you grep logs quickly during incidents. The threshold setting batches packets, reducing context switches. Real-time statistics tell you what is happening right now. The watch command updates every second, showing packet counts for your critical rules. During an attack, you will see specific counters skyrocket. The contract count shows connection table usage. If it approaches your maximum, you need to act. The SS command reveals connection distribution per IP, quickly identifying attackers. The metrics collection script runs every minute via cron, capturing long-term trends. It records packets dropped, connections rejected, and blacklist sizes. The RRD tool storage creates efficient round-robin databases that do not grow infinitely. After graphing this data, you will see attack patterns. Many attacks follow schedules, hitting at the same time daily. The alert thresholds require tuning for your environment. Start with conservative values and adjust based on false positives. The packets per minute drop threshold catches moderate attacks without alerting on normal rate limiting. The connection table alert at 80% gives you time to respond before exhaustion. The blacklist growth alert detects distributed attacks that slowly add many IPs. Integration with your monitoring stack is crucial. We send metrics to Prometheus, alerts to PagerDuty, and logs to an ELK stack. This gives us dashboards showing attack patterns, automatic escalation for severe attacks, and forensic capability for post-incident analysis. During one memorable attack, these tools helped us identify that the attacker was rotating through a botnet of IPs every 30 minutes, letting us adjust our defensive strategy accordingly. Performance optimization. Even the best DDoS rules are useless if they consume so much CPU that they become a DOS vector themselves. Let me share hard-learned lessons about optimizing IP tables for maximum performance under attack. Rule ordering is critical, as it is the difference between checking every packet against every rule versus early termination. Always put whitelist checks first so trusted traffic bypasses everything. Then, check blacklists to drop known bad traffic immediately. Connection tracking comes next. Established connections should skip further checks. Only then apply expensive operations, like string matching or rate limiting. During one optimization, simply reordering rules reduced CPU usage by 60%. Raw table processing happens before connection tracking, saving massive CPU cycles. Dropping invalid packets here prevents them from creating connection tracking entries. This is especially important for spoofed packets that would otherwise consume connection table slots. The NOTRACK target disables connection tracking entirely for specific traffic, useful for high-volume stateless protocols like DNS. Kernel tuning makes a huge difference. Expanding the connection tracking table prevents drops, but uses more memory. Plan 350 bytes per connection. The TCP syncookies setting is your emergency valve when the SYN backlog fills. Reducing timeouts frees connections faster, but might break legitimate long-lived connections. The netdev_max_ backlog increase prevents packet drops during traffic spikes. Hardware optimization often gets overlooked. CPU affinity pins network interrupts to specific cores, preventing cache thrashing. With multiple NICs, I distribute them across CPU cores. Receive side scaling, RSS, spreads packet processing across cores. On a 16-core server, proper interrupt distribution improved packet processing by 4x. Disable hyperthreading for network-intensive workloads. Real cores perform better than logical ones. The benchmark results show real-world impact. With optimized rules and tuning, a modest 8-core server can filter 10 million packets per second at 50% CPU utilization. That is enough to handle most attacks that make it past your upstream provider. More importantly, legitimate traffic continues flowing with sub-millisecond latency even during attacks. Emergency response procedures. When you're under attack, every second counts. Having well-rehearsed emergency procedures can mean the difference between a brief service degradation and hours of downtime. Let me share the battle-tested response plan that has saved countless services. The immediate response script is your panic button. When attack traffic is overwhelming your server, you need to act fast. The emergency rules block all traffic except critical services, typically just SSH from known IPs. This gives you breathing room to analyze the attack without losing server access. The rate limit is extremely aggressive, dropping 99% of new connections. It is harsh but keeps the server alive. Attack analysis must be systematic. First, identify the attack vector. Is it volumetric, protocol, or application layer? The commands shown quickly reveal attack patterns. Top source IPs show if it is distributed or concentrated. Port distribution reveals the target service. Packet sizes can identify amplification attacks. The TCP dump capture gives you forensic data for later analysis without overwhelming your disk. The graduated response escalates defenses based on attack severity. Level 1 is normal operations with standard rate limits. Level 2 increases rate limiting and enables additional filtering when you detect unusual traffic. Level 3 implements strict rate limits and geo-blocking when under moderate attack. Level 4 is crisis mode. Only whitelisted IPs can connect. All other traffic is dropped. Each level is a separate script you can activate quickly. Recovery procedures are often overlooked, but they are crucial. After an attack subsides, you cannot just remove all rules immediately because attackers often return. The gradual recovery script slowly relaxes restrictions over 24 hours. It monitors for attack resurgence and can quickly re-escalate if needed. The blacklist is preserved for 7 days to prevent immediate re-attacks from the same sources. Documentation during incidents is vital. The response log template ensures you capture all critical information: attack start time, type, intensity, mitigation steps taken, and effectiveness. This becomes invaluable for post-incident review and improving your defenses. I've used these logs to identify attack patterns and even track down attackers through law enforcement. Thank you for your attendance. Please consider subscribing to the channel.